So here we are at the cathode ray tube oscilloscope, and this device works essentially as a graphical voltmeter. You see a small dot going across the screen. The dot is moved vertically by the application of a voltage at the input. It's moved horizontally according to a time-based generator here. If I turn this up fast enough, that dot becomes a blur, and you see what appears to be a solid line across the screen. What I'm going to do is put it back in the dot mode and just review how this can represent a voltage graphically. If I connect it to a 9-volt battery, I touch ground lead to negative and probe to positive, I see the dot go in the up direction. And if I reverse my polarity, of course, it's going to go in the down direction. Kind of like an analog voltmeter with a zero-centered needle that can go positive or negative. What I want to show you now is another feature that's very, very critical for measuring signals, and that is the DC ground and AC switch right here. Every channel on the oscilloscope, every input, vertical input channel, has a DC ground AC coupling switch. If I set it to the ground position, and I try reconnecting my battery, we're going to see a whole lot of nothing. Absolutely nothing happens. I reverse the polarity, and nothing happens there either. There may be times where I have a signal applied to the input of the oscilloscope, and I want to basically turn that signal off and just see where my 0 point is. I can do that by switching to the ground position. Or if you're feeling devious, you can play tricks on other people and switch to the ground position and see how long it takes them to realize that. Then there's also the AC position. Now the AC position is a little bit trickier, and we're going to see what happens when I switch to AC. If I connect my battery here, ground to the negative, and probe to the positive, watch what happens to the dot. It goes up and then comes down, which seems very odd. When I let go of it, nothing. If I go to the positive side now, with my ground and negative on the probe, I shoot down and then I decay to 0. Anyone familiar with electronics realizes this is a capacitive discharge curve. You see a sudden spike up when I make the connection, and then we see an RC time constant sort of curve as it curves down towards 0. And that's exactly what's happening. We have a capacitor that is now connected in series with this input when we're in the AC mode. And what that means is that it's only going to couple AC signals into that channel. On the DC mode, we have a straight wire connection. And so what happens here is when I make a connection to a battery, it's like having a straight wire into a voltmeter. And so I can make my connection and the dot remains at a fixed height. However, in the AC mode, as you've seen before, I make the connection, it shoots up, and it comes back down in a curve. This is why this is important. I'm going to give you a quick demonstration here. Most oscilloscopes have a built-in square wave generator we're going to connect to. If I connect to this, what I see is a blur as the dot moves up and down very rapidly at about 1,000 cycles per second. I'll increase the size of that, and I will turn up my sweep so we can actually see this as a square wave. And you can see the classic square wave shape right there. We are in DC coupling mode right now. I can show you what ground looks like. Switch to ground, I simply get a flat line centered around 0, and I can make sure I'm centered exactly at 0 for purposes of measurement. If I go to DC, we see that this signal is really a DC pulse. We go positive, down to 0, positive, and down to 0. But there may be times where I want this oscilloscope to center the waveform. In other words, I want to get rid of the average DC component and only look at the part that varies back and forth. And I can do that by switching to AC. When I do that, you can see how the wave centers itself with that same sort of RC time constant approach that we saw with the dot. Now, even though this is a pulsed DC waveform, it appears to go positive above the 0 line and negative below the 0 line, because that capacitor in series with our connection has now blocked the average DC signal. So all we see is the back and forth component. This becomes very useful to us if we're measuring a signal that has a large DC offset with a small amount of ripple. If we want to view that small amount of ripple, we can switch to the AC coupling and have that center around the 0 line and then magnify it to our heart's content. If we leave it on DC, that bias will shoot it right off the screen if we try to magnify it. That's a very important feature. But it's easy to get yourself into trouble too if you leave it in the AC position and then you start measuring very low frequency signals, or worse yet, you try to measure something DC like this battery and you find, oh, what's happening there? My battery just died? Nope, it didn't die. We have it on AC coupling. You have to remember to keep it on DC coupling. And now, we're able able to measure that steady DC voltage. Okay.
Hang on, I won't show.